Hello everyone, welcome back to Chempoetry. In today's class, we are going to discuss a very important topic from Mass Spectrometry, Ionization Techniques. Now, before understanding different ionization technique, we need to answer one simple question. Why do we need ionization in mass spectrometry? A mass spectrometer does not directly analyze neutral molecules. The molecules have to be converted into ions because the mass analyzer separates ions according to their mass to charge ratio or M/Z. So the basic journey is sample, then ionization, then mass analyzer, detector, mass spectrum. Today we will mainly focus on field ionization or FI, which is an important soft ionization technique. But now let's first classify the ionization technique. Broadly, in mass spectrometry, ionization method can be divided according to how much energy is transferred to the molecules. The two important categories are hard ionization and soft ionization. In hard ionization, a relatively high amount of energy is transferred to the molecule. As a result, the molecular ion can be broken into several smaller ions. So, we get M to M plus radical, which is called fragment ions. A classic example is electron ionization EI. On the other hand, in soft ionization, the energy transferred to the molecule is much lower. Therefore, the molecule generally remains intact. We may obtain ions such as M plus S positive ion or M plus radical with comparatively little fragmentation. Example, field ionization, field desorption, FAB, MALD and ESI. So, remember this simple concept. Hard ionization is equal to more fragmentation. Soft ionization is equal to molecular ion preserved. This is difference extremely important for examination purpose. Let me ask you a question. If I want to determine the molecular mass of a compound and I want the molecule to remain largely intact, should I prefer hard ionization or soft ionization? Give me the answer below in the comment box. Then field ionization. Now let's come to our main topic. First, let's understand the definition. Field ionization is a soft ionization technique in which a very strong electric field is used to remove an electron from a molecule. In simple words, we don't bombard the molecule with energetic electrons as in electron ionization. Instead, we create an extremely strong electric field near a special electrode called a field emitter. This strong field causes the molecule to lose an electron. Here, M plus electric field gives rise to M positive radical plus electron. M represents the neutral molecule. When the molecule interacts with a strong electric field, one electron is removed. Therefore, we obtain the molecular radical cation, M plus radical. This is why Fi is called as soft ionization technique, because the molecule generally does not receive enough excess energy to undergo extensive fragmentation. Now we may ask, how strong is this electric field? The field strength can be approximately in the range of 10 to the power 7 to 10 to the power 8 volt centimeter inverse. This is an extremely strong electric field. How do we produce such a strong field? We use an emitter with extremely sharp microscopic tips. The sharp tips concentrate the electric field into a very small region. Think about a sharp needle. The electric field becomes highly concentrated near the sharp tip. This is the basic idea behind the field emitter. Now let's understand the instrumentation. The important components are field emitter, counter electrode, high voltage source, and mass analyzer. Let's understand them one by one. The first and most important component is the field emitter. Traditionally, tungsten or rhenium wares can be used, often with a surface containing very sharp carbon microstructure or microtips. Why do we need these sharp tips? Because sharp tips produce a very high local electric field. The second component is the counter electrode. It works together with the emitter to establish the required electric field. The potential difference between the electrode creates the strong electric field necessary for ionization. Next is the high voltage source. A high potential difference is applied between the emitter and counter electrode. The exact operating voltage depends on the instrumentation and emitter geometry, but the important point for focus is high voltage plus very sharp emitter equal to extremely strong local electric field. Once the ions are produced, they cannot simply go directly to the detector. First, they enter the mass analyzer. The mass analyzer separates the ion according to their mass to charge ratio. Finally, the separated ions reach the detector, which converts the ion signal into a measurable electric field. So the complete sequence: first sample injection, then enter to the field emitter, and then the ion formation, and then mass analyzer, then detector and spectrum. Now let's understand the actual mechanism. In step 1, molecule approaches the emitter. A gaseous molecule comes close to the very sharp emitter tip. Because the field near the tip is extremely strong, the molecule experiences a high electric field. Then in second step, electron tunneling. Now come the most important concept. The strong electric field modifies the potential barrier experienced by the electron. The electron can tunnel through this barrier toward the emitter. Therefore, the molecule loses an electron. After losing the electron, the molecule becomes M plus radical. So, M gives rise to M positive radical plus electron. This molecular ion is then accelerated into the mass analyzer. Now let's look at the mass spectrum obtained using field ionization. The most important features is the strong molecular ion peak. We can represent it as M positive radical because Fi is a soft ionization technique. There is generally much less fragmentation compared with hard ionization methods such as EI. Therefore, the molecular ion peak can be very useful for determining the molecular mass. What is molecular ion peak? Suppose a compound has molecular mass 100. If field ionization produces the molecular radical cation, we may observe a strong peak around the M by Z ratio equal to 100. This immediately gives us information about the molecular mass. Compare this with a highly fragmentation ionization method. If the molecular ion is weak or absent, determining the molecular mass can become more difficult. Therefore, the strong molecular ion is one of the more major advantages. Now, let's discuss the advantages. First, high molecular ion abundance. Because fragmentation is low, the molecular ion can be prominent. In second, minimal fragmentation. This makes interpretation of the spectrum comparatively simple. Third is molecular weight determination. The molecular ion gives direct information about the molecular mass. So, in one line, Fi is useful when we want to observe the intact molecular ion with minimum fragmentation. But every technique has a limitation. The first limitation is low ionization efficiency. Fi does not ionize every molecule efficiently. The second limitation is requirement for volatile or gas phase samples, since the molecules need to interact with the emitter in the appropriate gas phase conditions. Fi is particularly useful for volatile compounds. Therefore, it is not the best technique for every type of sample, especially large non-volatile biomolecules. So, today we learn the basic concept of ionization in mass spectrometry and then discuss field ionization Fi in detail. The most important things to remember are soft ionization, strong electric field, electron tunneling, molecular ion formation, minimal fragmentation, and finally strong field, electron out, molecular ions comes about. In the next lecture, we can continue with other important ionization techniques such as field desorption, FAB, MALDI, and ESI, and understand why modern mass spectrometry increasingly uses soft ionization methods for large and delicate molecules. If you find this lecture helpful, don't forget to like, share, and subscribe to Chempoetry. Thank you for watching. Keep learning, keep experimenting, and keep loving chemistry. See you in the next class. Thank you.